Hi guys, this video describes how we can implement the binary search tree algorithm as a recursive function. We're going to put two ideas together. There was the earlier idea of the binary search tree searching process, how you can search for a given key in a node in a tree efficiently. And we also saw in the previous video the linear recursion pattern on binary search tree nodes. We're going to put those two together and we're going to end up with a search algorithm that uses the linear recursion approach. Let's recap the binary search tree invariant and the search process from that earlier video. The binary search tree order invariant says that in a binary search tree, all of the keys in the left subtree have to be strictly less than the key in a parent node, and all of the keys in a right subtree have to be strictly greater than the key in a parent node. Or you could flip this around and you could say that all of the keys in the right subtree have to be greater than the key in the parent. Over here is a sketch of what that could look like. If I have a node with a key 61, then the invariant says all of the keys down the left child pointer into the left subtree have to be strictly less than 61. So you could have 8 or 37 or even 60 over there, but nothing greater than or equal to 61. And then vice versa on the right side, down the right child pointer into the right subtree, all of the keys down here have to be strictly greater than 61. So, 70, 102, stuff like that. The smallest key that could possibly be on the right side is 62. To search for a key Q, Q stands for query, which means what we're looking for. So to search for Q, starting from a node called where, we can use this invariant to make a decision about which way to go. There's three alternatives. What we do is compare the key Q we're looking for to where.key, the key in the node we are looking at right now. And this is a comparison between comparable types. So there's only three ways that comparison could go. Q could be equal, Q could be less, or Q could be greater. And based on the outcome of that comparison, we know exactly what to do. So if the query we're looking for happens to equal the key in the node, we found it. That's a successful search, and we stop. If Q is less than the key in the node we're looking at, then it's not there. We haven't found it. We need to keep looking. But the only place that Q could possibly exist is down the left subtree. So we can keep searching on the left side. We don't need to ever bother looking on the right side of this node because there's no chance that Q is over there. And the third and final alternative is if Q is greater, then the only place Q could exist is down the right subtree. So there's no point in searching on the left side. We only search on the right side. Keep looking there. We will see both recursive and iterative implementations of this algorithm. And we'll see that they have pros and cons. This is an interesting case where it's good to compare and contrast the two alternatives. They both work and they're both efficient, but they have some pros and cons, some advantages and disadvantages that we'll see in some time. So let's recap the find operation that we're trying to implement. The purpose of our binary search tree for now is to implement the map abstract data type. One of the major operations of the map abstract data type is called find. Find is given a key to look for, and you try to find that key in the map, and if the map contains a pair with that key, then you return that pair. That's a successful search. Otherwise, meaning the key is absent, we throw an exception. So that's what we're trying to implement in our binary search tree. We're going to be given a key to look for, and we need to find the pair, the key value pair, matching that key in the tree. And if we can't find that, we throw an exception. We're going to use the linear recursion pattern from the previous video. And the default base case for linear recursion on binary search tree nodes is to say when the where pointer reaches null, then you stop, and that's the base case. And in our situation, that corresponds to a failed search. So if I were to search for a key that's not present, how about 57? Then we would start at 37, go to the right to 61. 57 is less than 61, so we go to the left 55. 57 is greater than 55, so we go to the right. Well, now we fall off the bottom of the tree into a null pointer. And the reason that happened is because 57 does not exist anywhere. According to the binary search tree invariant, there's only one place where 57 could legally exist, to the right of 55, and there's no 57 there. So 57 can't possibly exist. So that's one base case. If our where pointer becomes null, we know the search failed. There is no such key. We're supposed to throw an exception in that situation. There's kind of a second base case. The base case is when you don't continue the recursion. So the second base case is when we found what we're looking for, when the search succeeded. So if the key we're looking for happens to be the key inside the node we're at, then the search succeeded. We're supposed to return the pair that contains that key, and that's it, no recursion. The general case is when we need to keep going. We haven't found what we're looking for, but we're not certain that it doesn't exist yet, so keep looking. And we recurse into one of the two children. So we decide, do we recurse left or recurse right, and we make one recursive call into one or the other of those pointers, and we make that decision based on how the comparison between the key that we're looking for and the key in this node goes. So if key is less than where's key, we recurse left, keep going to the left. Otherwise, we keep going to the right. So here's how this would look like in code. We've got a recursive function that needs an argument to a binary search tree node. We need a pointer to a node, and the node pointers are private to the BST class, just like with linked lists. So this cannot be a public function as written. So as usual, we have a public function that starts the recursion. The public function is just given a key argument, no other arguments, and it calls the find recursive function with the same query and starts on the root. So that's just a one-line function that starts the recursion. On the left here is a private helper function that actually does the search that we talked about on the previous slide. So we're given the node to start searching in, the key that we're looking for, query, and we return a reference to a std pair of key value type if we can find it, or throw an exception if we cannot find it. So the first base case is if not where. That means where is null, and in that case the search failed and we throw an exception. If we get past that, then where is a pointer to an actual node, and we decide if the search succeeded. So if the query we're looking for happens to equal where's key, then we found it, we're done, and we return where's contents. Remember that where is a pointer to a BST node. BST node has a contents, which is a pair with a key and a value. So this is the successful search right here. And then if neither of those base cases applied and we get past that, then we know that we need to keep looking. So if the query we're looking for is less than where's key, we return find recursive where left, comma query. Else, I'll mention that at this point in the code, we know that query has to be strictly greater than where key, so I don't test for that again. I don't say else if query is greater. There's no point to that, because if query was equal, we would have stopped the function here. If query was less, we would have gone into this return. So if we get down to this line of code, we know for sure that query is greater than where's key. We don't need to bother testing for that again. So we return find recursive where right, comma query. And that's it. That does the whole search algorithm. One thing I'll mention is just let's think about what this find recursive call does. So this is in the case where we're keeping looking. So in the less than case, we do a find recursive on where's left. So that means keep searching on the left side, and this will either return a pair if the search was successful, or this call will throw an exception in a base case later on. So this return here has that same effect. It either returns a pair of a matching pair, or it throws an exception based on what happens deeper in the tree. Let's go through an example just to visualize how this works. Let's say we look for 83. So first we would have a find recursive on the root, which holds 37, and that would be the greater than case down here. So then we would pause the execution of the find recursive on 37. That's paused on this return statement, waiting for the recursive call to finish. Then we would do a recursive search at 61. And we would say, how does 61 compare? Well, 83 is greater again, so we would execute this return statement at the bottom here, find recursive where's right, comma query, and pause that while we execute find on 83. And then where is a pointer to this 83 node, so query would match here, and the find on 83 would return where's contents, which would be the pair containing the key 83 and some value associated with that. So that gets returned. Then we would go back to the find on 61, which was waiting on this line of code for that find of 83 to finish, and a pair reference is returned. So then the 61 function call returns a pair reference back to the 37 function call that's still waiting. So the 37 function call is waiting here. It gets the same pair reference and returns that back out. So that's the outcome, is a reference to the pair stored inside the 83 node. If we did 57 instead, we would get kind of a different outcome. So we would start at 37. That would be the greater than case at the bottom. So we'd recursively search in 61. 57 is less, so we'd recursively search on the left side of 61. Then we would search at 55, and 57 is greater, so we would recursively search to the right of 55. Then we would hit this base case, not where. So at that point, we would throw a range error exception, and that range error exception is not caught in these recursive calls. They don't have a try-catch block, so that exception would throw all the way back out again to the original call that was searching at 37. Let's make a couple observations about this before we go on. So we are following the linear recursion pattern. Again, there's base cases up here, and then at most one function call on a input that's smaller, meaning a tree that's one level less high. I would say this is pretty readable. I think this code corresponds pretty closely to a description of what's happening. So if I say I want to search in a node for a given key, well, if the node is empty, then I can't find it. If the node has what I'm looking for, we did find it. And if the key we're looking for is less than the node's key, then look on the left side, otherwise look on the right side. So this reads pretty well. I would even say it's elegant. I think there are 4 cases in the logic for what's happening. There's 4 if statements, and they're all one line and pretty easy to follow.